In the mid-1990s, a team of meteorologists drove straight into supercells, armed with radar trucks, weather balloons, and a fleet of instrument-covered Ford Tempos. This was Project VORTEX, the bold experiment that forever changed how we understand tornadoes. If you've ever watched a tornado warning scroll across your TV or sprinted to shelter as sirens went off, VORTEX is part of the reason that warning came in time. It's the project that taught meteorologists exactly what makes a tornado touch down. But out there on the Great Plains, the atmosphere is complicated. Some storms look perfect but stay harmless. Others break every rule and drop violent tornadoes seemingly out of nowhere. So what did the VORTEX scientists discover inside these storms, and how did it rewrite our understanding of tornado genesis? Up through the early 90s, the biggest advancement in understanding tornado formation came with the invention of WSR-88 Doppler radar. For the first time, meteorologists could see the speed and direction of rain droplets within thunderstorms, with the standard velocity display showing rain blowing away from the radar station as red and rain blowing towards the radar station as green. Where these colors meet and intertwine shows rotation within the storm and possibly even a tornado. But the radar beam is angled half a degree above the horizon, so the further away the storm from the radar station, the higher aloft the beam. Coupled with the Earth's curvature, you might be looking at rotation 7,000 or 8,000 feet above ground level. With tornadoes occurring only a few hundred feet off the ground, meteorologists wanted to bridge that gap between the observable rotation aloft within a thunderstorm and the tornado on the ground. There were countless instances where significant rotation was observed on radar high above the ground, but no tornado ever touched down. So how would they tackle this massive problem? Well, supercells, the storms that produce tornadoes, are very dynamic systems that involve the complex transport of heat and moisture from the surface to 50,000 feet within a 5 to 10 mile radius. To the southeast of the storm, cold air is expelled via the downdraft. Directly to the south, warm inflow rushes into the storm's updraft. And to the southwest, cool, dry air crashes down to Earth in the rear flank downdraft. These three transports of air are constantly changing in intensity, and so being able to measure things like air temperature, pressure, and dew point surrounding the storm could possibly show some key indicators that may predict the exact moment a tornado would touch down. And more importantly, meteorologists were on the hunt for higher resolution data. They already knew the parameters that could help predict when a tornado could occur, such as storm relative velocity, which measures the wind shear, or the turning of winds with height, which could indicate the likelihood of rotating thunderstorms, or the Bulk-Richardson number, a ratio of atmospheric instability to wind shear, which could indicate a perfect environment where discrete storms could form while rotating freely. But these parameters were calculated via weather balloons, launched hundreds of miles apart. Small-scale disturbances like a little pocket of cool air near the surface can drastically change the favorability of tornadoes in between these data points, and meteorologists would never know, unless they brought the weather instruments to the storm itself. And so by late 1993, a series of hypotheses were created, all of which pertain to the atmospheric environment surrounding the storm, the formation of a tornado, the evolution of a tornado, and even how debris is lofted into the air. If the government was going to fund this tremendous undertaking, they wanted to cover as many bases as possible. Before we jump into VORTEX, I want to show you the shoes that have carried me through the chaos of November, my Vessi Stormburst sneakers. These have been my go-to whether I'm out filming, running holiday errands, or trying to stay warm in that brutal northern Ohio wind chill. They're warm, breathable, totally waterproof, and incredibly comfortable. Whether it's sleet, rain, or snow, they keep your feet completely dry thanks to Vessi's Dymatex waterproof technology. I really put these to the test last week. I wore my Stormburst to the Wednesday show, and I ended up standing for almost 4 hours straight. And somehow my feet felt amazing afterward. No soreness and no aching. These are the perfect concert shoe. They're also the most versatile shoe I've ever worn. Put them on after breakfast, and they just roll with whatever your day becomes. Whether it's shopping, hiking, or getting slammed around by a crowd of 20-somethings, the Stormburst can handle it all. And pick up the Vessi socks. They're moisture-wicking, super cozy, and pair perfectly with the Stormburst. So if you've been looking for the perfect gift, now's the time to buy. Everything is on sale, 25% off site-wide, and select styles up to 55% off. You get free shipping over $110, 30-day worry-free returns, and a 1-year warranty. Go to Vessi.com or scan the QR code on screen. Stay comfy this winter with Vessi. Between April 1st and June 15th, 1994, on days where tornadoes were likely, mobilize meteorological instruments such as pressure and temperature sensors, weather balloons, and Doppler radar, mounting them on both land-based vehicles and aircraft to gather data in and surrounding supercells in southern Kansas, Oklahoma, and northern Texas, creating a mobile mesonet. The vehicles in question must be simple, reliable, and aerodynamic, with the instruments being mounted high enough to not be influenced by the vehicle itself. And that vehicle was the 1993 Chevrolet Corsica. My, how the mighty have fallen on hard times. Atop the fleet of 15 sedans sat an RM Young wind velocity sensor, a Vaisala HMP 35AC temperature and relative humidity sensor, and a PTB 205A pressure sensor, all hooked up to a Campbell Scientific CR10 data logger. This ran through an RS-232 serial port to a 25 MHz Gateway 2000 Notebook 386 with 4 whole megabytes of RAM and an 80 megabyte hard drive. The laptop offered a real-time display archiving the raw 6-second data while deriving other variables such as the dew point and equivalent potential temperature. This was the pinnacle of technology in the mid-1990s. Each of the sensors were placed in a PVC tube with a fan to help shield them from adverse weather conditions. Additionally, a Motorola PVT6 GPS was used to obtain universal time, latitude, longitude, altitude, and vehicle velocity. So, with all that technology, were they successful in gathering data in 1994? Well, there were a lot of bust days early on. Days like April 14th, where although there was a decent dry line moving through central Oklahoma with dew points in the 60s ahead of it, no storms formed at all. Or days like April 26th, where supercells and tornadoes did occur, but they were outside the vortex target area of central Oklahoma. But on May 6th, the team finally got a win. A high precipitation supercell near Ralston, Oklahoma. The team deployed the mobile mesonet surrounding the southern flank of the supercell and managed to drive a 3mm Doppler radar van directly into the notch of the storm, a rain-free area just ahead of the rotating wall cloud. This was huge. It was one of the first successful notch deployments of a 3mm Doppler radar, and the high-resolution data could show the wind patterns surrounding a wall cloud in great detail. However, the team also noticed some issues. The rain in the storm was so heavy that the radar beam couldn't penetrate more than a few hundred meters into the storm. This meant that tornadoes wrapped in rain might not be possible to scan. But would the team be able to find a low precipitation tornadic supercell before that June 15th deadline? On May 25th, a classic dryline setup looked imminent in north-central Texas. The fleet deployed near a bulge in the dryline, wanting to study how storms evolved along the boundary. But this time, they carried a frequency-modulated, continuous wave Doppler radar. This lightweight, high-resolution system could allow them to sample a tornado every few seconds from close range. Converging on what appeared to be the dominant supercell, they successfully scanned a dusty cone tornado right as it touched down about 5 kilometers away. The data from the continuous wave radar was used to calculate the wind spectra every 78 meters in range from the radar to the tornado. This was the first time a mesh diagram of wind spectra could be created in such detail. It was also observed that while the mid-level rotation stayed relatively consistent, the low-level rotation ramped up right before the tornado dropped. The clear separation between the two was noted. By June 15th, the team only had a couple decent tornado intercepts, and more often than not, the lack of roads were preventing the vehicle fleet from collecting the types of sought-after data. Storm chasers know there's a lot of aimless dirt roads in Oklahoma and Texas, and if anything, the team realized they were able to consistently forecast where a rotating supercell would form, but they had little to no idea why some of those supercells produced tornadoes and others did not. But the vortex proof of concept was there, and so the hypotheses were refined for the upcoming 1995 season. The team would shift their focus from initiating boundaries like the dry line to specific tornadogenesis conditions, identifying processes within individual storms that could influence when or how a tornado would form, like a surging rear flank downdraft or a sudden change in storm structure. The vehicle fleet would also be updated, switching from the Chevrolet Corsica to the 1993 Ford Tempo, offering more structural rigidity and a stronger roof. By dumping resources into mapping out the exact locations of existing boundaries on severe weather days, the team could concentrate the mesonet on a much smaller area, increasing the likelihood of a successful tornado intercept. With all that being said, even if you're the best meteorologist on planet Earth, storm chasing involves a decent amount of luck. And while the 1994 season lacked in good fortune, 1995 more than made up for it. On April 17th, cool air from a morning line of storms spilled into the Red River Valley. The Vortex Armada rushed towards Burn Burkett, Oklahoma, intersecting this boundary just as a supercell exploded to life. It meandered northeastward, dropping several weak tornadoes as it attempted to anchor to the warm inflow. As the storm crossed the Red River into Oklahoma, it made a hard right, traveling due east, which allowed the Vortex Armada one shot at intercepting the wall cloud. Traveling north from Temple, the fleet attempted to get in front of the storm when suddenly a stovepipe tornado touched down and raced towards the road.
That's very close. Shoot tornado.
Half the team continued north, attempting to outrun the twister.
Come on, go north. Go north. Come on, boy. Go north. Ah, that's gonna take that. Very close. Oh my God, I took a sign or something. Watch out for debris from this side. Yeah, be very careful. Put your heads down.
The lightweight Ford Tempos would be no match for the 120-mile-an-hour winds, but thankfully, disaster was averted. The team had collected airspeed, temperature, and pressure data from less than a half-mile away from a young tornado, another huge win for Vortex. But the deviant motion of the storm was too dangerous to continue operations, and so the fleet disbanded. With several tornado intercepts under their belt, the Armada was in search of the Holy Grail, a large, violent tornado with a decent road network nearby. May 7th looked promising, with a stationary boundary in the Texas Panhandle and plenty of moisture and wind shear, but the storms would be moving at over 50 miles per hour due to the blazing fast winds aloft. They would have one shot at intercepting a tornado along this boundary before it would race off to the north. Unfortunately, they chose the wrong target. A secondary squall line to the east broke off into multiple discrete storms, with the southernmost cell growing into a monster supercell. A tornado touched down and tracked 50 miles through Ardmore, Oklahoma before occluding and lifting. The team left once again empty-handed. Now, while the armada of Tempos with comically tall sensors collected data on the ground, the Severe Storms Laboratory also commissioned a Lockheed P-3 Orion aircraft to fly around the target supercells, equipped with an Eldora radar system. The radar was mounted on the tail of the aircraft and could produce a full disk image of the storm surrounding the aircraft. Eldora allowed meteorologists to see warm inflow rushing into a thunderstorm, or even the invisible dry line, the physical boundary where thunderstorms would form. The goal was to map out the various air currents within the upper regions of a thunderstorm while the radar trucks scanned the storm base from below. By doing this simultaneously, they might be able to see how rotating winds high in the thunderstorm eventually become a tornado on the ground. And on May 16th, they got a glimpse into this mystery. The target was southwest Kansas. A clear dry line had formed in eastern Colorado with deep moisture to the east, and an approaching trough would give just enough lift for a few supercells to pop before sunset. The Armada and P-3 converged on this supercell, scanning the clouds as it approached Garden City. Just before 7 p.m., a thin, dusty tornado touched down a few miles from the team. The data collected from this tornado would reveal something incredible about how a tornado forms. Prior to the tornado occurring, rotation was present within the storm. 3,400 meters above the ground. There was also rotation present near ground level. However, the low-level rotation was about 8 kilometers southeast of the mid-level rotation. Additionally, this low-level rotation occurred along an existing boundary. This boundary was not created by the storm itself, but rather existed within the air mass as the storm approached. There was a clear disconnect between the two, but as the storm became organized, these two separate areas of rotation aligned vertically. However, a few minutes before the tornado, scans revealed a burst of cold air rushing towards the surface, wrapping around the wall cloud. This is known as the occlusion downdraft, and it's a separate feature from the rear flank downdraft, and it's influenced by a pressure gradient. As soon as this happens, the larger low-level mesocyclone breaks down into several smaller circulations, and when one of those circulations rotates beneath the updraft, that rotation gets stretched vertically and becomes a tornado. The remarkable complex dance between thermodynamics and kinematics had been documented by high-resolution Doppler radar from both the air and the ground. But again, this was a weak tornado. The team was desperate for a Southern Plains monster. And then came June 2nd. A sharp dry line would push east throughout the afternoon, initiating a line of supercells along the boundary. The Armada closed in on Clovis, New Mexico, but the initiating storms were messy and unorganized. But as the sun approached the horizon, the southeasterly winds near the surface increased dramatically, and the storms began to rotate. The Armada followed the storms up US 60, when suddenly, Probe 5 found itself in the path of a developing monster. This was the tornado the team had been searching for the past 2 years. With the Armada surrounding the supercell, sampling the inflow winds, both aircraft scanning the storm from above, and a Doppler on wheels scanning the tornado from close range. This would be the best raw data of a violent tornado ever collected for exactly 90 minutes.
It's almost touching the ground now. It's coming down. Coming down. Coming down. It's a beauty.
The southern cell had strengthened and was approaching the small town of Dimmitt, Texas.
I'm afraid it's going to max out. We might want to get a little further north, actually. Watch, keep an eye on that, Bob.
The resulting Doppler on wheels imagery of this tornado would show the clearest image of tornadic winds ever documented up to that point in time. It showed the asymmetry of the tornadic wind field in great detail and proved that close-range mobile radar could show the entire picture of winds surrounding a tornado. Additionally, a strong outflow boundary existed near the Dimmitt cell right as the tornado touched down. It was yet another example that reinforced the theory of enhanced rotation along these surface boundaries. The Texas Panhandle became extremely active that week, and on June 8th, the Vortex team got their final intercept of a mile-wide tornado near Allison, Texas. This was the same day as the Pampa tornado, which will be covered in a future video. The data collected by Vortex in 1994 and 95 would be used in countless research papers over the next 10 years, and the conclusions led to one of the greatest leaps in history of our understanding of tornado genesis. Vortex showed that tornado genesis depends heavily on both the storm structure and the storm surrounding environment. Tornadoes are aided by boundaries, some of which are so shallow they're nearly invisible. The boundaries enhance rotation in the lowest level of the atmosphere, which is then tilted and stretched upwards, becoming a tornado. If the low-level and mid-level rotation don't become vertically aligned, a tornado won't occur. The occlusion downdraft comes from inside the mesocyclone and triggers a breakdown of the parent rotation into smaller vortices. one of which drifts beneath the updraft and becomes the parent tornado. Finally, mobile Doppler radars were revolutionary in showing the entire wind field of a tornado in great detail. These findings laid a foundation for modern Weather Service tornado warning operations, giving meteorologists clear ideas on what to look for when forecasting tornadoes. The legacy of Vortex will never be forgotten. Thank you for your time. If you'd like to send me weather-related items or a letter, my P.O. box is on screen.